All right, so chemistry. Just a show of hands, what students have had chemistry before? Okay, about 75%. Good. We're not going to do a lot of chemistry in the sense of doing like a whole year's work. It's just not ready for this course. But it's things that are basic. And then we'll talk about things that are more pertaining to biology. A whole chapter on something called organic chemistry, actually a couple chapters. So we want to gear it towards biology. All right? We're not going to be dealing with things like nuclear reactions and stuff like that. It's just too overwhelming for a course like this. So today is just basically the anatomy of an atom and bonding and things like that. So if you had that, this will be a good review for you. And I got a few mnemonics to help you out with this. This joke may or may not make sense to you. I'm hit, I've lost an electron, are you sure? I'm positive. Some of you may get that. Some of you will say, well, it has something to do with positivity. I don't exactly know what it means. I assure you, by the time we get to the end of this PowerPoint, you'll understand what that is. But I think a lot of students have problems with chemistry, mainly because you really can't see it. I mean, when I do anatomy, I mean, if I talk about the ear or the heart, you can see it, and you can imagine what the pressure does inside the heart, because you can see it. Chemistry is beyond, you can't even see it through a microscope. So you have to visualize everything. And that's difficult to do for many students. So we got to deal with facts, and you have to put all these facts in your head and try to visualize things. And that's what's difficult, I think, mostly for students. But then there's a set of students that love it because there's a lot of math. But we're not going to do that much math here. A couple of things, but there isn't much math to deal with chemistry, or biology for that matter. If you take the chemistry that the other students are taking, it's loaded with math. So there's no calculator needed for biology here. So, why do we have to do chemistry? What's the big thing? Why do we have to do this chemistry thing? Well, there's a lot of chemicals that are compose your body and the entire biosphere. And they're the basics of everything. I mean, if you don't understand how water works, then you're not going to understand how an organic, like a fat, the foods that you're eating get broken down and if they can get passed into a cell or not. So you need to understand how water works. But in order to understand how water works, we need to do basic chemistry. So I promise, I'm just going to do the mere basics. All right, this is about 70 slides. I just knocked off 4. Isn't that a good feeling? All right. All right, let's do very basic stuff. Math. Okay? It's anything that takes up space. That's it. Anything that has a mass is going to be matter. Whether it's something solid, something liquid, or something that's gas. That's going to take up space. You put an empty balloon, there's space in there, but you put gas in there, it's going to take up space. Okay? And mass is this measurement of how much space an object takes up. Now, the question is, do you weigh the same here on Earth as you would on the moon? There's something different here. But aren't you the same person you are here when you are on the moon? Right? You got the same parts, you got the same skin, you got the same hair, the same heart, same nose. So the mass is the same. What's different about this? The weight, right, the gravitational pull. Okay? Mass versus weight, they are not the same thing. They're related, but they aren't the same thing. Okay? Mass is a measure of matter. You're still occupying the same amount of space on Earth as you do on the moon. You didn't collapse, you didn't expand. Okay? Weight, we have to throw in the gravitational pull. So it's a combination of weight and gravity. The moon is smaller, so the gravity is not going to pull you as much down to the center of the moon. So you're going to weigh less up there. And in fact, I went to the Museum of Natural History about a couple years ago, and they went to the astronomy section over there, and they had a scale. You weigh on the scale, and I'm weighing like 100, and then I go over on here, and it's like I weigh 24 pounds. And that's a scale which will feel like on the moon. So you know I'm trying to get all my astronomy under my belt so I can move there, and that's, I don't know if people know how much I weigh. And this is the basis, I believe I'm saying this, but this is the basis of Superman. Krypton, where he came from, was a humongous planet. Right? Think of Jupiter, we're probably bigger than that. So he was born and not raised, you know the whole story about Superman. I won't have any questions about Superman. But he was over there, so he is used to that. So he probably weighed a whole lot. Then he comes over to Earth, which is like a dot in this room. So he weighs like nothing. So he could jump from here to another place and fly to get there, because he doesn't weigh much as we would be on the moon, and it looks like we're flying. That's where the concept comes in. I don't know if Stan Lee actually, or whoever, not Stan Lee, I don't know, Marvel versus DC, whoever came up with Superman. But that's the basis of what that is. Does that make sense? All right? So, and also too, I don't want to get into it, but even if you go to the North Pole, because you're further from the equator, it's a little bit flatter up there, you actually weigh a little bit less. Not much, we're talking about a pound or two, but Santa Claus sure likes it up there. You know, that's why he gets bigger and bigger, because he doesn't weigh that much. Okay? So we have different states of matter, solid, liquid, gas. It's pretty easy. I think most of these have understand what solid, liquid, gas is. I'll show you in essence what that is. We also have something called plasma, and I really don't want to spend too much time on that because it really doesn't do much. It doesn't relate much to biology. Plasma is like a plasma screen. It's a little bit different, but I'm not going to go talk about plasma. There is a fourth. I don't want you to go back to high school and tell your teacher, oh, he says there's only three. There is a fourth state of matter called plasma, which doesn't really relate much in biology. And if you know anything about anatomy, that is not the same plasma that's in your blood. Okay, it's a different thing. So a solid has a definite shape and a definite volume, like this pen. Stays the same shape, stays the same volume. No matter if I drop it over here, move it over here, it's the same shape. Okay? The particles inside, which we'll get into, they stay close together. And that's why it stays as a solid state like that. Okay? They don't have much areas to move. We have a liquid, and I'm not going to demonstrate that, but you can visualize it. You take milk, it has a definite volume. You can see it in the bottle. You pour it on the desk over here, the shape changes. It's not a bottle shape anymore. But it's still the same volume that you put there. That's because the particles are moving further apart of each other. Then you have a gas. Put smoke out there. It doesn't have a definite volume. It's all over. And the shape is all over too. That's because the particles are moving further away from each other. Okay? Now, I want to talk a little bit about energy. It's the capacity to do work. All the things that I just mentioned, solid, liquid, gas, they could do work. They could release energy and do something. Well, it puts matter into motion just the way a slinky would. A slinky, when you hold it out like this, it has the potential to move. Keep in mind that word potential. When you let go of it, it's actually moving. And if you do that a lot, it gets hotter because it's releasing energy. So we have two types of energy. Kinetic energy, that's energy that's moving. And we have, like I said before, potential energy. Energy that has the, sorry to use this in the definition, the potential to do work. The slinky, you pull it out like this, hold it there, it's got a lot of potential. Once you let go of it, kinetic energy is happening. Okay? So we'll be talking about potential kinetic energy throughout. Now, matter can change shape, and you've seen this kind of stuff, right? Go from a liquid to a solid, that kind of stuff. So solid, liquid, and gas. If you want to change that, we're going to have to add energy, and that's pretty obvious. You take an ice cube, right? Do that. Take an ice cube, you put heat to it, energy, it's going to turn into a liquid. More heat, it'll evaporate, right? I mean, you put heat into it. The other way, a gas to a liquid to a solid, you have to remove the energy, the heat, right? Put liquid in a freezer, not hot in there. You're not letting the energy go up, so you're going to subtract it. Now, state changes, you know about these. I'm going to go really fast with these, so I think you're pretty obvious. Evaporation, liquid to a gas, right? Condensation, cold soda, and you see that it's cold, and then the heat from the sky is going to condense the gas to the water vapors to the liquid, and you see beads of water on your soda. So it condenses on there, freezing, pretty obvious, and melting, right? But there's also two other ones. And this one you can see a little bit. These ones you might not have heard about. Deposition. Deposition is going from a gas to a solid. You're skipping the liquid state. It's turning carbon dioxide into dry ice. Ooh. We should have had some dry ice here to really do some wonderful stuff. But you're turning it into dry ice. And you've probably seen the dry ice, right? You go to these haunted mansions and stuff, and they drop some this carbon dioxide into water, bubbles, and you got smoke coming out. Right? It's carbon dioxide gas, right? Then we also have sublimation, and it's the opposite. You're going from a solid to a gas. It skips the liquid state, and it's what I just explained to you. You're taking a dry ice, which is solid, and you turn it into a gas. It skips the liquid state. There's even some printers, these newer printers that are coming out, those sublimation printers. Are you familiar with that? No? What they're doing is, they're very, very expensive, $2,000 to $3,000 if not more. And what it is that the ink itself is a solid. And then they're doing I don't know how they do it, but they do something where it just turns into a gas, and the gas or the steam per se goes onto the paper, and it does it that way. And you get crisp pictures doing it that way. So maybe in 20 years, the regular consumer can buy one of these things. All right? All right, so let's talk about atoms. These particles that we've been talking about, moving further apart or closer together. What's that all about? All right, we have atoms to elements to molecules. Atoms is the smallest thing that anything can be broken down to. Okay? More or less, they're identical building blocks for each, what we call elements. An element is the simplest form of matter with unique chemical properties. They all have the same, all these atoms have the same properties with each other. We also have a molecule. And a molecule is made up of two or more of either the same or different elements. You're going to see a lot of chemical symbols. There's something called a periodic table. That's kind of like why I'm wearing the tie today. Okay? There's something called a periodic table. You have to understand how it works, and I'll show you what it is, but I've developed this course where you don't really need to read it, but understand how it works. Okay? And you can get information there. And I do not expect you to memorize those things on it. But there's going to be some chemical symbols that you'll need to memorize, but it'll be so easy because we're going to be using them so often. Like C for carbon, Na for sodium. Why is it an SO? Because it's a Greek word. Natria means sodium, and they just carry that way. You also learn a lot of other ones like that too. Potassium is a K and stuff. Now, we combine things when it comes to compounds and molecules. Remember what a molecule is. It's a combination of two or more of the same or different atoms or elements. A compound sounds like the same thing, but they're definitely from different elements. So what's happening here is that we can have, and this will make more sense when we go through each chapter, but we can have oxygen binding to another oxygen, something called a double bond. We'll get into that later. So we have oxygen going to oxygen. This is definitely a molecule. It's two elements that are connected to each other. But it's not a compound. If we deal with water, water is H2O, right? Water is going to be two hydrogens connected to a different element, oxygen. Now, water is a molecule, but it's also a compound. Is that clear? Okay? All right. And there's some other examples there that you can see. Sodium chloride, carbon dioxide, and you'll get to know those quite often. Now, this is the four most common elements of the human body. You should know these. Carbon, hydrogen, oxygen, nitrogen. There's the symbols for them. I had a teacher of biology in 9th grade, and I'll always remember it. His name was Mr. Seishon. He said, "You'll always remember my name because the last four letters of his name always will be the most common elements in the body." And I still remember it. He's probably dead now, but I still remember it. Thank you. So do know those. And that makes up about 96% of your body. Okay? The other elements that are in your body are what we call trace elements, which are going to be less than, well, be about 4%, but some are only like 0.1% and things like that. You do not have to memorize those in a sense of which ones are trace, because if you know which ones are the main ones, then everything else is trace. Okay? And I kind of just put them up there just to show you to be complete with this. Okay? Iron is one, calcium is one, these other ones. So what is this atom that we've been talking about, right? This neat little thing. How they came up with this whole idea is beyond the scope of this course, let alone it's beyond the scope that I could ever imagine. But there's three parts to an atom. There's the inner core that's made up of what we call protons and neutrons that you see on this picture in blue and red. And then you have this thing that's swirling around. We call them orbits or shells. These are electrons. They're all important, but the electron, I think, has a little bit more importance because that's the one that's going to be dealing with bonding. So the nucleus, protons and neutrons, the electrons, which is much smaller than the protons and neutrons, orbits or floats around the nucleus in these what we call orbit or shells. And you've seen typical videos, something like this going on. A proton has a positive charge to it. A neutron has no charge. And then, well, you do that one, because if you know the other two, you know this one. Okay? This is very important when we got to deal with electrolytes and ions. You need to understand why is a sodium a positive charge and why a chloride is a negative charge and so forth. The key is the electron is negative. We'll get back to that. So the atom nucleus, these protons, atoms are classified by the proton number. That's what determines what element we have. Changing this number means you've just created a new atom or element. Normally, the way it works, normally being stable, the number of protons equals the number of electrons equals the number of neutrons. Normally, however. Neutron number may change. Look at this over here. The protons, now this is hydrogen, helium, and something called lithium. Hydrogen has, well, if you look at the red up here, okay, look at the red up here, there's one proton here. In helium, there's 2 protons. In lithium, there's 3 protons. And that's what determines if this is a helium atom or a hydrogen atom. The number of protons. But keep in mind the yellow, which are the neutrons. They don't need to be equal to the protons, but yet it's still going to be hydrogen. It brings about the topic of isotopes. Isotopes is if a neutron number changes, but the proton number remains the same. Remember, you change the protons numbers, you got a whole new element. Changing the neutron number is the basis of what we call nuclear chemistry, which again, I'm not going to go into with you. But understand, if you want to get into radiology, you're going to need to know a lot about chemistry. If you like chemistry, that might be the career you want. But it's important for radiology. Now, all isotopes of one element react the same way chemically because they all have the same number of electrons. For instance, oxygen has 8 different isotopes, but each function identically in metabolic reactions. They weigh differently, because everything has weight to it, including neutrons and protons, but they all work the same way because there's the same number of electrons. All right? Isotopes can be stable or unstable. So let me show you what this is. Here's 3 isotopes for hydrogen. It's all hydrogen because there's one proton there. There's one red thing in the middle. But look at the neutrons. There's none here, there's 1 here, there's 2 here. So it's all hydrogen, but they might have different names to classify which isotope it is. Deuterium and tritium over here. Again, you don't have to memorize those things and what happens to them, but you need to understand the concept that neutrons can change. Let's briefly talk about radioactive isotopes, because there is a part here I need you to understand when we deal with something called carbon dating. Radioactive isotopes is unstable isotopes. Atom's nucleus decomposes and releases energy. When they decompose, trying to go from unstable to become stable, it releases energy to do that. This energy is what we call radioactive. Like gamma rays, you've heard those. And these can be measured. Now, this radioactivity can be used clinically in the medical realm. We use it for imaging purposes. We use it to track hormone uptake, because we could tag certain things. We could tag iodine that our thyroid uses. And we could follow it using imaging. We could see if a lot of it went into the thyroid or very little. It lights up on the screen. We could see it. It's used for power supply for pacemakers, people have heart problems, and also for treating cancers. So go into radiography, if that's your nick, then super. It also is used to date relics of past life, fossils. So, in order to understand this carbon dating, let's just talk briefly about something called a half-life. A parent isotope, all right, the beginning isotope, decays into the daughter isotope, right? It's going to go from unstable to become stable. The unstable is the parent, the daughter will be the stable one. And it does this at a fixed rate. It doesn't go like this. It goes at a fixed rate, whatever it is. The time it takes 50% of that isotope to decay is a half-life, thus the name half-life. And each radioactive isotope has a distinct half-life. It's not affected by environmental variables like temperature, pressure. They have no effect on this. It just does it automatically. So we have this, what we call carbon dating or radiometric dating. A measured ratio, we measure the ratio of different isotopes. You calculate how many half-lives in years that have passed since the organism was fossilized or a rock was formed. And that's what this is. Some isotope half-lives are seconds to days. Those are the ones we'll use for cancers and radiography. You don't want something that's going to take years. That person's going to be radioactive. You want it to go in, do the image, and let it go out. Otherwise, it starts ruining things. You start looking like a mutant man and stuff. So some isotope half-lives are centuries or longer. For instance, uranium-238 has a half-life of 4.5 billion years. Moon rocks are about 4.5 billion years old. So therefore, we know that the moon is the same age as the Earth. Can we work with that? So the Earth's been here only for 4.5 years. Well, no, 4.5 billion years. Carbon-14 is the one that we use for fossils. Let me look at that. Okay? That's all I want to say about isotopes. Does that make sense about that? And fossils? Because we'll be using words fossils throughout in carbon dating and what carbon's doing. We'll talk about environmental stuff and this global warming carbon. Carbon's good, but carbon can also be bad. All right, so definitions. Atomic number. That's how many protons you got. We just call it the atomic number. Okay? The mass number is how many protons and neutrons are in there. And the atomic weight, it's also known as the atomic mass, that's the average of the mass numbers of all the isotopes. We measure it in what we call the units as Daltons. So if there's 8 isotopes for oxygen, then they take the average of those 8 isotopes, and that's going to give you your mass number. And that can be found on that periodic table that I'll talk about. So if I give you the mass number, and I give you the atomic number, you should tell me how many neutrons are there. Or, because you did basic algebra, if I give you the number of neutrons, and I give you the mass number, I could also ask you how many protons is in there, right? By just rearranging that. So be sure you can do that. You don't need a calculator, and we'll give you simple numbers, but that's an easy algebraic equation. That's fair? Right? We can do that. Okay. So this is our periodic table. And you can see certain things on here. Every periodic table will have certain things. A lot of other periodic tables will have just those certain things and a bunch of other stuff on it. But just to show you, and it's very organized about how they're doing on here. I'll show you briefly how that is, but again, this is not a chemistry class. I'm just going to introduce you to it. But you could see all the different element symbols all over here. Hydrogen's right up there with the H. So the chemical symbol for potassium is K, it's right here. You'll see a number, like for lithium on here, you'll see a number 3, that's telling you the atomic number, how many protons are in there. You'll also see there's another number, it's usually in decimal point form, but there's the atomic weight. And those are basically, those are the basics that you should find on every periodic table. When you go into chemistry and become a chemist and do all that, you'll probably have a lot of this memorized. Not because you had to, but because you use it so much.